Hey guys, so I'm Faisal Iqbal. I'm a software engineer for Cisco Systems, and I'm going to talk about data plane monitoring and segment routing networks. Unfortunately, Clay can't join me, so you'll have to live with me. So data plane monitoring, of course, is very near and dear to most of the operators. You want to make sure your network is functioning correctly, everything is going the way it should, there are no traffic black holes or other faults happening in the network. So for most of the slides, I'll just use this topology over here. So it's pretty simple. I'll be describing it, don't need to basically memorize it. So black holes occur when a router starts dropping traffic, and it could be that we are dropping, it could be for a single prefix, it could be just over a particular link, it could be all the traffic over the network. And there are multiple reasons that it could occur. Sometimes there's a forwarding inconsistency where one of the network, let's say one of the line cards is a bit behind, it doesn't have the latest update. Sometimes the control planes of the two devices can get out of sync. And user can also, of course, can make a mistake, misconfigure, and that could lead to a black hole. So there are various causes. It's a significant pain point and something that we want to address in any decent OEM solution. So I'll just highlight this using a very simple example. So here we have a VPN, which C device C1, which wants to send traffic towards CE2 over the MPLS network. So in this case, it will send the packet to node 1. So node 1 will slap the transport label and the VPN label, and then send the packet towards next hop. So if you notice over here, the label, MPLS label that is being sent, it is unlabeled on the next hop. So, and this is not a very uncommon scenario in the network encounter. So in this case, it may just pop that label and just expose the VPN label prematurely and send it towards the next hop. And because, of course, the next hop is a core node, it does not understand the VPN label or the payload underneath it, it's going to drop the traffic. And in MPLS networks, typically, it could also happen that you have ECMP in the network, and in this case, you may send the packet towards incorrect node, and that will lead to a black hole as well. With segment routing, the labels are global, which means that most of the network devices understand the labels. So even if the traffic is not sent to the correct node, it may still end up reaching the destination, but not through the expected path. It may take a path that is probably longer, or maybe introduce congestion in the network, or it may even break SLAs. So this is what I'm using as path divergence. So again, I'm going to highlight it using an example over here. So here, let's say we have a policy where we want to send the traffic from node 1 to node 7 through node 5. So in this case, we can have an MPLS label stack where the first label, 16,005, is the label to reach node 5. And then the next one is labeled to reach node 7. So node 1 builds this packet, send it toward the next hop, 3. So 3 is a penultimate hop. So it's supposed to pop the label and then send the traffic towards 5. But let's say there was an issue in 3. So instead of popping the label and sending it towards node 5, it instead sent it towards node 6. And because the packets still have 16,007, node 6 will pop the label, it understands it, and send it towards 7. So now the packet did reach the destination, but it is not taking the path that we expected it to take. And that can lead to congestion and other issues I mentioned above. So currently, there are various fault detection mechanisms available for operators. Broadly, we can categorize them as proactive, which means they are constantly scanning the network and making sure everything is working the way it should. But for large network, that gets really complicated because it's tough to proactively monitor the entire network very easily. So then operators have to also rely on reactive tools as well. So in reactive, you get alerted by a fault, and then you start use your arsenal of OEM tools to identify the fault and the point of failure so you can take a corrective action against it. And then we can also say that the tools available to you right now, they could be local, which means that they just rely on the node. They don't send any probes or anything outside the box. So for example, some routers and switches have a label or route consistency checkers, which make sure that label or routing database is in sync with fib. But on the other hand, we have LSP ping or BFD. And these tools validate the entire LSP. So if something is broken, BFD can monitor it proactively at a very fast rate, and LSP ping it's not meant to be constant, very fast rate, but it can detect more faults and various other use cases as well. But overall, we can say that in this case, these tools are incomplete because they only identify a subset of faults. For example, BFD, LSP ping, they cannot detect path divergence because packets still reach the destination. So it will report everything is OK. And then there are also scalability challenges with it because you have high number of ECMP and ECMP combinations. So it just gets into an ECMP explosion. It's nearly impossible to monitor every single path end to end. So we think that we need a tool that can complement the existing tool set that can, well, we're not going to go away from end-to-end monitoring or local tools, but we can come up with something that complements them to monitor more fast that can remain otherwise undetected. And for this purpose, we are introducing segment routing data plane monitoring. So SR-DPM is an independent solution that allows a node to test its entire forwarding path end-to-end in the sense that ingress to egress on the same device, not end-to-end in the network sense. For any MPLS traffic that could be received from any upstream towards any downstream ECMP. So in this case, we are not testing just one path. We're not just testing local probe and sending it out. We try to model the customer traffic exactly. And we do this through a distributed and localized detection mechanism that is based on source routing paradigm. So in this case, it can monitor the entire network. It can monitor the network proactively, constantly going on in the background, detecting any faults. And it's localized because we don't go beyond one hop. Each node just checks itself and then its immediate neighbors. It doesn't try to go beyond that because then we'll run into the same issues that we have with end-to-end tools. Instead, we can distribute the detection mechanism, detection over work to different devices in the network. So each device can just check itself and its neighbors, and you don't have to rely on just a single tool or one end-to-end mechanism. And because underneath, we use a specially crafted LSP ping packet. So LSP ping is widely supported by most vendors at MPLS level, and most operators probably who deploy MPLS, they use it every day. So you don't have to go to IETF, write a draft, standardize it, and hope that all your other vendors also support it. It's interoperable by design. And because we are relying on source routing, so in this case, source routing has adjacency set, which means that we can pin down exact interface or a link. So in this case, we can pin down the upstreams and downstreams, and using this, we can make sure that we test each upstream and downstream combination, because you could have multiple line cards, and maybe if you test just one of them, it doesn't mean that the other line cards are functioning the way it should. So now I'll go into the mechanics of data plane monitoring, where I'll highlight how it works. So broadly, it's a two-stage process, or how we call phases. So first, before the real work we want to do is we want to make sure that we are forwarding every prefix that can get from upstream towards the correct downstream node. But before doing that, we want to make sure that all our links are forwarding traffic correctly. It's not that let's say if one of the links is broken, then we'll see the same breakage across all prefixes, and we may think that it's an issue with the prefix when it's really a link issue. So we address this using adjacency validation. And once we have that one, then we'll also use it as a building block for our prefix validation phase. So here, adjacency validation, the basically idea is that you want to make sure that you are able to send and receive traffic correctly to each one of your neighbors. So here, let's assume that we have this topology again. So we are working on node 3. That is the only node that is running DPM. No other device in the network is running DPM right now. So in this case, it has links to neighbors 1, 2, 5, and 6. And right now, I'm showing only single links, but of course, you could have ECMP there as well on these nodes. So for each neighboring link, node 3 will construct an echo request packet that goes to the neighbor and then comes back on the same link. It will just transit through the neighbor. It will not get punted on the box. The box doesn't need to do any, the neighboring box doesn't need to do any software processing there. It will just simply switch the packet back to you. And then once we receive the packet, we can validate if we were the intent target. So in this case, for example, we have adjacency seed label, first one, 24031 to take it from node 3 to 1, and then 24013 will bring it back from 1 to 3. So if we receive the packet back, because packet will have enough information encoded in it, we'll know that we are the intent target and we received it on the correct link. Let's say if packet end up on node 4, then we'll receive a fault. This link is not functioning correctly. And we can do this for the remaining links as well. So we did it for node 1. Now we can do the same thing for node 5 using its own adjacency seed labels to and from, for node 6, and then node 2. So once we have that one, in this case, we know that all our links are functioning correctly. And again, I'm going to iterate that there's no software processing involved in the neighboring device. They're just going to switch the packet back to the DUT, in this case, node 3. Node 3 is the only one which is sending and receiving probes. So once we have that one, then we can identify if there's any malfunctioning link. So malfunction could be that maybe the link is dropping traffic. It could be that it is forwarding the traffic, either like the DUT or the neighboring device, it is sending it towards incorrect link or incorrect device entirely. So we can't use, if there's any malfunction, we can't use that particular link. We'll have to exclude it from our further validations. And also, we use this as a building block for the next phase, as you'll see. So prefix validation is what we really are interested in. We want to make sure that we are able to send and receive traffic from any upstream towards any of our downstream neighbor for that prefix seed, and we want to do it for every prefix seed in the network. And we achieve it by looping the traffic because we want to simulate customer traffic path. We don't want to just generate a probe locally from RP, send it out over line card, because then customer traffic doesn't take that path. Customer traffic comes on an ingress line card and then goes out via the egress line card. And we want to model that customer traffic path. So we do this by looping the traffic using the adjacency seed label we just discussed. And then using this looping, we can actually get the packet back on the device, and then we have a prefixed label. Once we receive the packet, the next label will be prefixed label, which will take it towards one of the downstream devices. So now for any, let's say like we have a DUT3, we can identify the upstream link and the downstream link for any prefix set, and if one of them is malfunctioning, we can exclude it. So in this case, for any prefix set, we'll go through this process. So here we have, for each upstream and downstream combination, the DUT, in this case, the device under test, node 3, it will build a packet, MPLS echo request packet, because that's what we use for this one. That will go to our upstream neighbor, comes back to us, and then expires at an immediate downstream neighbor. And we can set the TTL to 3 to make sure. That way, the packet doesn't go beyond one hop. We just go one hop up and then one hop down. And that way, we are just limited in this one. We don't have to worry about the scalability challenges of end-to-end mechanisms. And then we have the prefixed label, because when the packet comes back at the DUT node 3, it will only have prefixed label. The adjacency labels would have been popped. So in a way, customer traffic as well will have the same label. So we are forwarding exactly like any customer traffic would. And because we could have multiple ECMP, here we have 2 ECMPs. So we want to make sure that we can test each one of them separately. So LSP ping has 127/8 destination addresses, and we can play around with the entropy to make sure that we can test each one of them correctly. And once we send it out to the correct downstream, we want to make sure that it reaches there. Let's say like if hardware and software are out of sync, we thought we were sending it towards node 5, but it ends up at node 6, we can't detect that scenario. So we include enough information in the echo request packet that we can do that. So we include the ID of the destination that we are trying to reach, and then the information about the label stack that should be expected at the next hop, the interface on which the next hop should receive the packet, and of course the next hop ID. So we send this packet out, it reaches the downstream device, and then downstream can make sure that it has a labeled path to reach the destination. Here our destination is 7. So node 5 can make sure that it has a path to reach the destination 7, and that path is labeled. And then it can also make sure that it was the intended destination. We didn't mean to send a packet to node 6 and it somehow ended up at node 5, and it was received on the correct link. And this information, along with the information of the next hop from node 5, is sent back towards 3 in an echo reply. So this is standard echo reply here. Node 3 is not running DPM. It's not even DPM aware. From its perspective, it just received an echo request packet, and it is just replying to that echo request. So it could be a non-Cisco box. It could be running an older version. That's the beauty of it. It's interoperable by design. So once we receive the reply, we can make sure, okay, if there was any fault, then we can alert the operator that for this particular combination, we are seeing an issue you may want to monitor. And we can also, I'll talk about remediation as well. That's also possible. And then we can go on to test the remaining combinations. So here for the same downstream 5, the traffic could potentially come from the other upstream as well. And similarly, we can test it for the downstream 6, both combinations, and then for remaining prefixes as well. So that way, we can test each upstream and downstream combination for any prefix in the network. Right now, I've just described it for node 7. Okay, so as we saw, we are not going beyond one hop. So in this case, each node just takes the packet to upstream and then downstream, not beyond that one. So it will detect any forwarding because we are exercising entire forwarding chain at the DUT. So if there's any forwarding issue for the particular prefix head, we will detect that prefix that will detect that issue regardless of upstream or downstream neighbor that we have. And it can also detect most forwarding issues at our neighbors, at our downstream neighbors. For example, if downstream does not recognize that prefix head label, or it doesn't have a path onward, so it receives the packet with label, but it cannot send further with the label. It cannot send it unlabeled. We can detect that kind of scenarios as well. But if there's anything beyond one hop, so in this case, 7 or 8 or 4, they are not our immediate neighbors. So of course, we are not sending any probe to them, so we will not detect faults there. But DPM is meant to be deployed throughout. It's a distributed detection mechanism. So instead of deploying on a single node and trying to test entire network, instead you can offload the work to different devices. So you can deploy DPM at strategic nodes in the network to make sure you have a good coverage in the network. And of course, you want to make sure that operator gets a really good fault. Operator get a fault notification message, and that notification message is informative and accurate. So when DPM detects a fault, it will alert operator. It could be through a message on the box, or it could be through telemetry mechanism. But it will notify it, and that notification will contain the information of the fault. It will include the links that are involved, the prefixed label, as well as a brief error description of what really went wrong. So you can take, and we can also have a remediation action, because once we know all this information, we have effectively isolated the fault in the device. We know what's going wrong with which prefix, what are the nodes, and what are the links involved in this one. And then based on the error description, we can know that, okay, what particular message, maybe it's an unlabeled packet. Maybe in this case, the next hop is not being sent correctly. Maybe one of the devices is running slow. So we can take a remediation action let's say reroute the traffic, or reinstall the forwarding entry, etc. And then we will try to avoid fault as well. Okay, so far I have discussed this mechanism as a proactive, where it is constantly running in the background and then detecting faults. But we want to be flexible. We know that some operators, maybe they're running their own probes at a very high rate, and they don't want to run DPM very fast rate. Instead, they want to run it slowly over, but then based on certain network events, maybe they want to just test a particular prefix is installed correctly across all the line cards, across all the links. So you can test a single prefix, or you can test all prefixes. Or maybe you want to do it based on a certain network event. Because typically faults don't occur in steady states. Maybe a link went down, some new link or device got added, so now you have forwarding updates, your IGP converged, it's gonna install a bunch of forwarding updates on the control plane to hardware path. And that's where, in this when you're doing this installation, when you're installing these forwarding updates, that's where you can potentially cause issues, where it is gonna, if there's any bug, or maybe one of the line cards is slow, so it didn't get the updates, it's running stale version. Then when you have these kind of triggers, in this case, it could be a link going down, or an alert from IGP that it's converged, there's no further update for, let's say, a certain amount of time. Then you can run DPM to make sure that all the forwarding entries are installed correctly. It could even be a controller-driven trick, so we can let operator know that, okay, whenever they send a particular trigger, then we can monitor a set of, or all the prefixes in the network. Oh, my bad. So in conclusion, we believe that DPM is an innovative solution to data inconsistency and identify any traffic black holes in the network. Instead of trying to do end-to-end fault detection or try to test all the possible combinations, instead we distribute the detection work through the devices in the network, where each node just tests itself and its immediate neighbors. And because we are using LSP ping, so it's interoperable by design. There's no standardization required. Your neighbors doesn't have to be running a particular version of the software or a particular vendor, etc. As long as they are able to send and receive echo replies and echo requests, they should be able to work. And we are not planning to, as I mentioned earlier, we're not intending to replace existing tool set that you have in your arsenal. They have their own place, they're really suitable. We are not trying to be BFD. We're not trying to be LSP ping or discovering all the possible paths in the network, etc. Instead, we believe this tool complements the existing solutions that operators may have, and then instead of replacing them. And of course, it is ready for adoption by customers. We are working very closely with some of the customers. So in this case, Bell has joined us as the co-author of this talk. And if you have any question, I'll be very happy to answer these questions. I guess that's it.
Andrei Kostin, Tixavi. Have you done any scalability testing for this solution?
Yeah, of course. So scalability is very important. The thing is, you could have some networks maybe running few hundred or even less than 100. Other could be running thousands of prefixes. So yes, scalability is an important concern, and we have various tuning parameters, because in the end, we want the solution to be flexible. So in this case, you may want to have a solution where you can tune the detection interval, you can tune the packets per second that we are sending with. So using these tuning parameters, we plan to cover up to several thousand of prefixes. We can discuss separately, but I can give you the numbers on that one. And of course, for each one of them, we can have a high number of ECMP as well, upstream as well as downstream.
Okay, thank you.
Okay, I guess you guys have 5 minutes.